to a little introduction on infinite summations. So we're going to start with the following picture of a square. Each side has length 1, and so the area inside the square is 1 centimetre or 1 metre squared. Now we're going to add to the picture. We're going to first of all divide it into 4 equal squares as shown, and then shade the lower left square. And what we're going to do now is repeat exactly what we've done, but in this upper right hand square here. So divide it into 4 and shade the lower left part. Now imagine you keep going. There will be the next square, the next, the next, the next, and so on. Now this process could carry on forever because there's always going to be a little room left in which you can split into 4, shade the lower left, and then go again in the upper right. You never quite reach this corner. So it's kind of an infinite or iterative process that we have going on here. So what about the area that we've shaded? Write down the area of each of the blue squares. So the first one that we shaded here in the lower left corner, well, that was a quarter of the original square whose area was 1. So the area here is a quarter. The second square we shaded here, well, that's a quarter of the size of this one, a quarter of a quarter. So that would be a 16th. And the third time, it's a quarter of the size of the previous square. So 1/64th. So the pattern goes like this. A quarter for the first shaded square, 1/4 squared for the second shaded square, 1/4 cubed for the third shaded square, and so on. So, as I mentioned, in theory, we could kind of draw these blue squares carrying on forever, never quite reaching the corner. But I want you to imagine that we could carry on forever, and we did reach the corner. The question is, how much would we have shaded? What fraction of the large square would we have shaded in blue if we could really carry this on until we reach the corner? So here's a nice way to spot. You don't need a formula or anything. Just spot that this blue square is matched by this red square above it. Same for the second, the third, the fourth, and so on. But also matched by these green squares to the side. And that would carry on all the way up to the corner if we could really complete this process. And so what we have here is the original big square split into 3 equal colours. So, to answer the question, the blue shading that we had originally must constitute a third of the total area of the big square. But writing that mathematically, we could say that this infinite sum, a quarter, the area of the first square, plus 1/4 squared for the area of the second square, plus 1/4 cubed, plus 1/4 to the power 4, plus, and so on without end. That's what I've written here, and the plus dot 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 just indicates that that pattern carries on without ever really stopping. But if we could carry on this pattern to its completion in the corner, we see that we would have added the entire blue area here would have added up to a third. So what we kind of see in the picture here is that a quarter plus a quarter squared plus a quarter cubed plus a quarter to the power 4 and so on all would add up to a third if we could carry this sum on forever without stopping. Okay, so something just to have a little try at. Could you make a similar picture? You could use a square to show this sum. A half plus a quarter plus an eighth plus a 16th plus carrying on forever would sum to 1. And starting from the above sum, can you think of an infinite sum which will add up to any number that you care to think of? So the way to do that would be just to play around with what you've got here and try to adjust it so that the left hand side is an infinite sum adding up to whatever you want it to add up to on the right hand side. And just to finish, here's an example of an infinite sum that shows that infinite sums can behave quite strangely. So here's a pattern of numbers: 1, 1/2, 1/3, 4, 1 over 5, you see the pattern carries on like this. What I'm going to do next is alternate the signs. Start with a plus and then a minus, plus, minus, so it goes like this. And the dot 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 indicates that that pattern really carries on forever without stopping. Now it can be shown that that does indeed add up to something. You might like to try it in Excel for a few thousand terms. It's not too tricky, or it won't take too long to do that, and just kind of convince yourself that this will add up to something. But what I'm going to do now is just have a play around with these terms. So the first term, 1, I'm going to write as 2 minus 1. That hasn't changed anything. The minus a half, the second term, let's leave that as it is, but the plus 1/3, let's write that instead as 2/3 minus a third. That hasn't changed, that's still a third. Minus a quarter for the next, plus 1 over 5, let's write that as 2 over 5 minus 1 over 5, so we've still, in the bracket there, got a fifth. And the idea is to do that all the way along. And that would be the same summation. What I'm going to do next is divide this number, this a here, by 2. And I'll do that on the right hand side just by going along the terms and dividing them all by 2. So first of all, the 2 divided by 2, minus 1 divided by 2, minus a half divided by 2, plus 2/3 divided by 2, minus a third divided by 2, minus a quarter divided by 2, 2/5 divided by 2, 1/5 divided by 2, minus a sixth divided by 2, and so on. Now what we've got here is, if you have a look along the original sum, every term that you see here appears again down here. So for example, the 1 at the start is still at the start. The minus a half comes next, as it does below. The minus a quarter is in the 4th position here, but the 3rd position down here. The plus a third, which was 3rd here, is 4th down here. Minus 1 over 6, minus 1 over 6. Minus 1 over 8, minus 1 over 8. Plus a fifth, plus a fifth. In fact, everything that's here will appear exactly once down here. So effectively what this trick has done is just take this series, this infinite sum, and it's just jiggled up the terms, so they're being added in a different order, but we can see that just by adding them in a different order, we've affected the value of the answer. We've now got precisely a half of the original value of the sum. And that's one of the strange properties that can happen with infinite summations, unlike ordinary finite summations where the order of summation doesn't matter, it doesn't affect the result. But for infinite sums, sometimes you've got to be careful. The order in which you add can change the result. So, hope you found that interesting, and thanks for watching.